Yeah. Good evening, everyone. Thank you all for being here. This is Yashasvi Julakanti, currently pursuing PhD in astronomy and astrophysics at Vergata, and I'll be chairing today's seminar. Let me introduce you today to today's speaker, Dr. Anna Ho. Dr. Anna is currently a Miller postdoc fellow at the University of California, Berkeley, USA. She has been awarded her PhD from California Institute of Technology, or Caltech, USA. Dr. Anna works in time domain astronomy, and her research primarily focuses on a search for exotic stellar transients. She's been awarded the prestigious Springer Thesis Prize for her PhD thesis on the landscape of relativistic stellar explosions. And today she is here with us to talk about fast transients, a fleeting window on the final stages of stellar evolution and formation of compact objects. Thank you very much, Dr. Anna, for being here today with us. I think we can dive right in.
Okay, great. Thank you for the introduction, and thanks for the invitation to join and give a seminar today. And good morning from California. Oh, I'm sorry. Can you hear me okay?
Yes.
Oh, okay. Sorry, I thought I heard something. Okay, so I know that this audience has a broad range of scientific backgrounds, and so I thought I would start by providing some very broad context. We have this textbook story in astronomy that the fate of a star depends primarily on its mass. The story goes that massive stars end their lives by developing an iron core. This collapses, and neutrino irradiation causes the star to explode in a supernova, which has a characteristic kinetic energy release and ejective velocity. And the story also goes that this mass determines the nature of the corpse, the compact object remnant. But recent developments, particularly in observations of the explosions themselves, which I will generically call transients, are forcing us to confront the fact that the story needs to be rewritten. That the fate of a star depends, of course, not just on its mass, but also on a whole set of parameters and processes that we don't understand very well. Supernovae themselves can have a huge range of kinetic energies and ejective velocities. There are observational hints that a significant fraction of stars shed a significant fraction of their mass shortly prior to core collapse, and we don't know why this is. We don't know what parameters determine whether a star will explode at all, or whether it will collapse directly and form a black hole, or whether it will explode completely, leaving behind nothing at all. We'd also like to know the relative contribution of different mechanisms for causing the explosion. There's not just neutrino irradiation, there can also be fusion, or what's called a central engine. So this engine refers to tapping into the rotational spin-down power of a newborn neutron star, or the accretion power onto a newly formed black hole. And finally, we'd like to know why some massive stars do weird things, such as make gamma ray bursts, and this ultimately requires a better understanding of the basics of stellar evolution. So for me, the ultimate goal is to establish a mapping between stars, the physics and appearance of the terminal explosion, and the properties of compact objects that we observe in the Milky Way. And these are what I see as some of the interesting and important questions that we can make significant progress on in the next decade. And I'll address a couple of these in my talk today. In addition to what they can teach us about stellar evolution, which I've already told you about, the reason I particularly enjoy working on astrophysical transients is that it's really their extreme properties that can teach us about very basic astrophysical processes. So in basically real time, before our eyes, on timescales from seconds to years, we get to witness the formation of a compact object, the launch, in some cases, of a highly relativistic flow and its propagation through matter, and the formation of a shock and the acceleration of particles at the shock front. And I'll address a couple of these topics today. So this brings me to the transients themselves. For the last century or so, the discovery of cosmic explosions has really been dominated by telescopes operating in the optical band of the electromagnetic spectrum. It's common to parameterize optical transients in terms of their timescale, shown here on the x-axis, and their peak luminosity, shown here on the y-axis. And until around a decade ago, there were basically three major established classes of events. But then, thanks to improvements in basically CCD technology, telescopes developed the capability to survey very large areas of the sky very efficiently. This resulted in the discovery of several new classes of events, filling in many of these kind of gaps in parameter space. And for my work in the last few years, I've been trying to answer questions that have required me to develop strategies for pushing to even faster timescales and higher luminosities. Now, there are a lot of extremely interesting phenomena in this part of parameter space. I don't have time to talk about them all today. So what I've decided to do is just focus on two of these topics in particular, starting with the landscape of relativistic stellar explosions. So in this first part of my talk, I'm going to give you an example of how we can use a time domain survey as an experiment to test a hypothesis. And so I'll first explain what this hypothesis is that we're going to test. This has to do with a very famous phenomenon called gamma ray bursts, or GRBs. And I know there are many, many GRB experts in this community and probably on this call as well. But I also know that not all of you work on GRBs, so I want to give some context. They are what they sound like. They're brief, intense flashes of gamma rays. The first one was discovered half a century ago, and thousands have been discovered since then by satellites such as Swift and Fermi. These are the brightest known photon sources in the universe. We can detect them basically all the way out to the other end of the universe, and their distribution across space and time is basically set by the cosmic star formation rate. At this point, we think there are two predominant channels for making GRBs, short duration GRBs from compact object mergers, and long duration GRBs from the deaths of massive stars. And it's the long GRB case that I'll be focusing on today. So I want to just walk you through the kind of traditional long GRB model. The idea is that the core of a massive star collapses and forms a compact object, neutron star or black hole. This acts as a so-called central engine. So accretion or rotation powers this ultra-relativistic flow that breaks out from the surface of the star as a jet and escapes into interstellar space. The gamma rays are thought to be produced by material, sort of collisions between material traveling at different speeds within the jet itself. And then the jet collides with the ambient medium. It sweeps up gas and dust, it decelerates, and it produces synchrotron radiation called the afterglow. This afterglow can be observed all across the electromagnetic spectrum, from X-rays to radio waves. It can be detected out to large angles away from the jet axis. But in order to see the prompt burst of gamma rays itself, the GRB, it's thought that we have to be looking directly down the barrel of this quite narrow, few degree wide jet. So we've come a long way in putting together a basic picture of GRBs. But there is a major outstanding mystery in this field that GRB satellites cannot solve, and that is the rate. So basically, what fraction of collapsing massive stars produce these relativistic jets? This question has many important implications. It has implications for how stars explode in the first place, because if present, the jet can contribute significantly to the explosion. It has implications for the origin of the elements. In particular, these systems are thought to be important sites of our process, nucleosynthesis. And it has implications for how jets are launched and the diversity of jets that can exist in nature. And yet, at this point, we're really only aware of GRBs themselves. GRBs are thought to be rare, so even correcting for the collimation, about 0.1% of supernovae are thought to make GRBs. But there are a lot of reasons to think that GRBs as we know them are actually just the tip of the iceberg. A lot of things have to go right to produce and detect a GRB. The jet itself has to have a very special composition, and then of course it has to successfully tunnel through and escape the star. And it's this first point here that brings me to the hypothesis that I want to test in my talk today. So I'll refer to this as the dirty fireball hypothesis, and here are the basic principles. So you can show that in order to get gamma rays from a gamma ray burst, the jet has to accelerate material to ultra-relativistic speeds, initial Lorentz factors of hundreds or thousands. And to do that through E equals gamma mc squared, so for a fixed E, to have a huge gamma, you can only have a very tiny m. And for these systems, that m turns out to be about an Earth mass, which, given that these are stellar mass scale, very dense systems, seems extremely unnatural. So it seems far more natural to think that most of the time the jet actually entrains more matter. In that case, it can only achieve moderate Lorentz factors. You won't get a gamma ray burst. You might get some kind of X-ray transient, and that's what we call a dirty fireball. As the hypothesis is that dirty fireballs greatly outnumber clean fireballs in nature, and the implication of this would be that GRBs are actually a rare case of a much more common phenomenon. How can we test this hypothesis? Well, the most direct way would be to look for X-ray transients, but currently we can't do that. And so for now, the best way is to look for the afterglow. So just to remind you, this afterglow is produced when the jet is decelerating and colliding with the ambient medium at synchrotron emission. And basically, by the time the jet has gone into this stage, it has sort of forgotten its initial Lorentz factor. And so if this prediction is correct, then the rate of afterglows in nature should greatly exceed the GRB rate. However, it is very difficult to find an afterglow if you don't have a GRB satellite telling you where and when to look. There have been decades of searches for afterglows in multiple bands of the electromagnetic spectrum, and until a couple of years ago, this had only amounted to a handful of candidate discoveries. The reason this is so difficult is that the gamma ray sky is relatively dark. So if you see a flash of gamma rays, that's probably a gamma ray burst. Whereas the sky in these wave bands is crowded with billions of sources varying on all timescales, of which afterglows are just a tiny fraction. So in the last few years, I've been working on developing a strategy for solving this problem. The first thing you want to do is actually detect the afterglow. This is a sample afterglow light curve, optical afterglow light curve. The x-axis shows time in hours, and the horizontal dashed lines show the sensitivity threshold of several different optical surveys. And the point is that the afterglow fades below the sensitivity threshold within just a few hours, and so you need to be sampling the sky on a kind of similar time scale. Then you have to actually identify the afterglows. So this is a collage of fast fading optical transients, and the basic message is that the primary false positive in this search, the kind of foreground population that you end up having to deal with, is flares from stars in the Milky Way, particularly M-dwarf flares on the shortest timescales and cataclysmic variables on somewhat longer timescales. And so there are various ways of dealing with this. One of the most important strategies I've found is to use the color in the optical bands. So in the optical filters, afterglow emission is optically thin synchrotron radiation. It appears red, whereas stellar flares are thermal and they appear blue. So you have a fast fading red transient. How do you confirm that it's an afterglow? The most important step is to get a spectrum. This is a spectrum of an afterglow, a recently discovered afterglow at a redshift of 2.5. And you measure this distance from identifying a set of absorption features in the spectrum. Okay, so in the last few years and currently, I've been applying this strategy to a survey conducted by the Zwicky Transient facility. ZTF is a facility hosted at Palomar Observatory in Southern California, and it's designed for very large-scale transient discovery and classification. So we use 3 different telescopes, the smallest one to actually discover the transients, and then the 2 bigger telescopes to systematically classify and characterize them. And in the last few years, I've been involved in several very large-scale efforts. We've been classifying all transients brighter than a certain threshold, so we call a magnitude-limited survey, as well as all transients within a certain volume, so a volume-limited survey. This is 1/64th of a real ZTF image. It has an enormous field of view of 47 square degrees, shown here compared to various other optical survey facilities. And on a given night, ZTF takes images as part of several different surveys down to a certain limiting magnitude. We're currently doing the entire night sky visible from Palomar, of course, every 2 nights in 2 different filters, and then a smaller area of the sky multiple times per night. The process of identifying transients is fully automated. So ZTF takes a new image, we subtract an image of what the sky normally looks like at that location, and then every 5 sigma change results in what we call an alert. And this is just a packet of code, and we're using the same format that will ultimately be used by Rubin. And just to give you a sense for the timescales, from the close of the shutter following an image to the availability of these alerts is just about 8 minutes. Okay, so now I want to make this more concrete for you by walking you through one particularly exciting night for me in the history of ZTF. So on this night, we had about 420,000 alerts from 370,000 unique sources. Of those, I would estimate that about 140,000 are truly real, so not some kind of artifact. There we go. I then require that each source have a minimum of 2 detections separated by a baseline of 30 minutes. And this is to get rid of moving objects such as asteroids. So zooming in on these 30,000 objects, I then try to get rid of as many stars as possible through a kind of crude latitude cut and also cross-matching with catalogs. And then I require that each source be young. So it's detected for the first time last night with a non-detection or upper limit the previous night. And at this point, the number of transients is very manageable. I've been leading an effort within ZTF along with my collaborators. We share responsibilities for scanning and conducting the follow-up observations. But on this particular night, it was my turn to scan. And looking at the 7 objects, I concluded that 2 were likely supernovae, 4 seemed to be stellar flares that had escaped previous cuts, and 1 was an excellent candidate for being an afterglow. So this is the subtraction. There was no known source, no known optical source of this position, down to a very faint limiting magnitude. And indeed, this was the first afterglow that I found with ZTF. So when you find a transient, it's randomly assigned a name. It's based on the year of discovery and then a string corresponding to the order in which it was discovered. So AAA, AAB, and so on. And this one, just by coincidence, turned out to be 2020 BLT. So BLT was found at a redshift of 2.9. It looked very much like a GRB afterglow, except that there was no associated detected GRB. I'll walk you through the timeline of our discovery and follow-up in days on the x-axis. We first detected this with ZTF at about 19.5 mag. I immediately triggered follow-up imaging, which confirmed that it was fading quickly. I triggered a target of opportunity spectrum on Keck using LRIS, and the window for my observation was at something like 4:30 a.m., so right at the end of the night. And I was worried that I would accidentally sleep through it, so I set myself up to sleep in the observing room at Caltech, and I took a picture of my sleeping bag here to commemorate this experience. So I got the redshift with LRIS and also detected X-rays with SWIFT and radio emission with the VLA, and that was it. So all the emission we detected from this transient was from data obtained within just about 10 days. And since then, this has been working very well. My search criteria have resulted in the discovery of 8 afterglows to date, the most recent one just earlier this month. And ZTF has found an additional 3 events, from searches for kilonovae and electromagnetic counterparts to gravitational waves. To my knowledge, these are the fastest optical transients discovered first in the optical band. Here they are on this optical transient parameter space. They span a wide range of redshifts, and they bring the number of optically discovered afterglows with redshift measurements from just 1 prior to ZTF to 8 today. And what's exciting for me is that this is really the first systematically selected sample of afterglows outside the gamma ray band. So what are they? The surprising thing for me, so every time there's an afterglow, I go back and I check, was there a detected GRB consistent with this time in this position? And what was surprising to me is that of the 11 events, 7 turned out to have associated detected GRBs. And what's more, you actually can't rule out that the others did too. So this is a plot showing the gamma ray energy on the x-axis and the optical luminosity on the y-axis. These points are just GRBs from the literature. These green points are the events with detected GRBs. And the purple points are what you could call orphan afterglows. These are the afterglows that had no detected GRB. But the point is that given the redshifts of these events and the coverage and sensitivity of GRB satellites, you actually can't rule out a GRB counterpart. So what does that mean? At this point, I'm sort of forced to conclude that this hypothesis that there's some huge population of successful relativistic jets that do not produce gamma ray emission cannot be correct. And I think this supports the idea that at least these successful jets are intrinsically quite rare. I think it teaches us something about the structure of these jets, that the opening angle of the emission that produces the gamma rays has to be similar to the opening angle of the emission that produces the early afterglow. And as for this dirty fireball picture, I think we're left with one of 2 possibilities. Either somehow a clean jet is intrinsic to the phenomenon of jet launch and propagation, or if these dirty jets do exist in nature in large numbers, they somehow look significantly different from regular GRBs. So for example, perhaps they don't successfully escape the star, or they emerge with a far lower energy per solid angle. So what do we do next? Well, for me, the fact that we've now shown that these at least fully successful highly relativistic jets seem to be intrinsically rare tells us that we have the opportunity in the next few years to finally settle this question of the rate. And so I think there are two things we need to do. We need to find the off-axis GRBs to measure the intrinsic GRB rate, and we have to get to the bottom of this mysterious phenomenon called low luminosity GRBs. And I'll say a bit now about these low luminosity GRBs because I think they're extremely interesting and extremely important for this story. So you might have seen these referred to in the literature as X-ray flashes. These are basically a subset of GRBs that have quite different properties. So in particular, the prompt burst high energy emission is typically softer in its energy, which is why they're called X-ray flashes sometimes. And they have kind of a smooth pulse, which is quite different from regular GRBs. And so one idea is that the mechanism for producing these GRBs is actually fundamentally different, that it's not some kind of successful collimated ultra-relativistic jet, but instead it's, for example, some kind of relativistic shock breakout. And what's very interesting about these events is that their volumetric rate seems to be 1 or even 2 orders of magnitude higher than regular GRBs. There are a few different ideas for what they could be. One of the ideas is that they are fully successful, but sort of lower luminosity, wider angle analogs of classical GRBs. One idea is that these are failed or unsuccessful GRBs, basically. So GRBs where the jet is choked. And another suggestion is that they are fully successful jets that are just viewed off axis. And so instead of seeing the jet, you're seeing the breakout of this kind of wider angle, mildly relativistic material. And so why don't we know what they are? Basically, it's because the rate of discovery is very low. So these events are basically the worst case scenario for existing GRB satellites. For example, my colleagues in Fermi GBM tell me that it would be very hard to distinguish such an event from their background evolution. And so even though they're probably intrinsically very common, at the moment, only a handful have been discovered to date. And so something I've been working on in the last couple of years is trying to figure out if we can discover these events using optical surveys instead of using GRB satellites. And I was inspired by this figure here. This is the very famous event, kind of the original GRB supernova, which also was kind of the original low luminosity GRB. And this is a plot showing the optical light curve in several different filters. So this is sort of a normal supernova light curve. It goes up and down on the time scale of weeks. But if you look at what's happening in just the first few days, there's some kind of initial flash, you could say, prior to the main rise of the supernova light curve. And so I don't have time to talk about this today, but long story short, I've been investigating whether we can use sort of searches for this early flash to find low luminosity GRBs more efficiently than we can with GRB satellites. But what I think will really solve this problem is X-ray surveys. So finally, in the next year or two, we will have the kinds of X-ray transient surveys that we need to really find low luminosity GRBs very efficiently. And these are also exactly what you would want, by the way, to find these hypothesized dirty fireballs. And so there are a couple of facilities that I'm showing here. One is Einstein probe, the Chinese mission. One is SVOM, the Space Variable Objects Monitor. It's a joint mission between China and France. And these are important because they have good sensitivity at lower energies, which is exactly what you want for this particular science. And just a very crude, doing a very crude estimate, I would predict that these surveys will find at least a few low luminosity GRBs every year at fairly low redshifts, if not tens per year, depending on what their intrinsic rate is. So I think the next few years will really be exciting because we'll finally have the chance to kind of solve this low luminosity GRB mystery and establish the rate of these relativistic stellar explosions. Okay, so that brings me to the end of part 1 of my talk. I've shown you how we can use an optical time domain survey to conduct an experiment and test a hypothesis. And now in the second part of my talk, I want to switch gears. I will show you how when we sort of push to new parts of parameter space, we can also discover things that we really didn't expect. So in this part, I'm going to show you a lot of radio data of transients. And I thought it would be useful to start with a primer on what radio data sort of normally looks like. so that you can better appreciate why what we did see was so surprising. So basically, when you have an explosion, you launch a shock. At the shock front, you accelerate electrons, amplify magnetic fields, and these electrons emit synchrotron radiation. This is the single electron spectrum. You make an assumption about the energy distribution of the electrons. The conventional assumption is that they have a power law distribution in energy. And to basically integrate this over that distribution, you get a net power loss, some nu to the minus alpha, which is shown on the right here. And then there's a critical frequency at which the emission becomes, or at which the plasma becomes optically thick to its own radiation. The spectrum turns over and you get this characteristic nu to the 5/2 power law. And we see these kinds of spectra in many areas of astrophysics, including in studies of supernovae. So here's the cartoon again. I'm now showing you data that was collected by a radio telescope called the Very Large Array, or the VLA. As a picture of me reproducing a scene from the movie Contact at the VLA. I don't know if any of you have seen that. But anyway, so here's the SED, or the spectrum, 3 weeks after the explosion. The VLA observes at frequencies from about 1 to 50 gigahertz. And you can see that in this epoch, the emission at these frequencies was completely self-absorbed. And then over time, the spectrum sort of shifts down in flux and in frequency, so that a year later, the same frequencies are now sampling the full shape of the spectrum. So now if you, maybe I'll go back to this. If you imagine observing at a single frequency, say 1 or 2 gigahertz, at early times you won't see anything because the emission is completely self-absorbed. But then as the SED shifts down, the light curve will go up. And then when this peak frequency passes through your observing band, the light curve will turn over and come back down. And so that's what you're seeing here. These are single frequency light curves of a very similar supernova. So what do you actually want to do scientifically? You want to measure, as best as you can, the frequency and flux of this peak. And that's because at any given time, this peak is set by sort of basic physical properties, such as the radius of the shock and the magnetic field strength. And if you have the shock radius, you're able to estimate the mean shock speed up until that time. By adding the additional constraint of conserving momentum across the shock front, you can estimate the ambient density and the corresponding mass loss rate of the progenitor system. And with the magnetic field strength, by making an assumption about the fraction of energy that has gone into magnetic fields, you can estimate the total amount of energy that has been thermalized by the shock. So a convenient way to parameterize radio data from supernovae is with the product of the frequency and time, and then the peak flux density. And those are the X and Y axes of this kind of classic diagram in radio supernova astronomy. So basically, on this diagram, you can, for every observation of a supernova, you can put it somewhere on this diagram. And these are all just, observations of various different kinds of events. There have been decades of these sorts of what I'll call low frequency radio observations of transients, and these have played a major role in our understanding of stellar death. They help to establish that GRBs come from supernovae, that even some kind of optically normal looking supernovae can actually harbor relativistic ejecta, and have helped us reconstruct the mass loss history of different kinds of progenitor stars, and have helped us learn a great deal about the dynamics of these relativistic jets. Okay, so that's the kind of context that I wanted to provide. And now I think that sets the stage for the topic of this part of my talk. So this story started in June of 2018, when the ATLAS survey, another optical time domain survey, discovered a transient that was coincidentally named AT2018COW. So we all immediately began calling this the cow, and this is a plot summarizing why this was so immediately interesting to the transient community. So this is a parameter space plot, same parameter space for optical transients that I showed you earlier. These color points are all just various established classes of supernovae. These black points on the upper left are sometimes referred to in the literature as fast blue optical transients. That's just because no one knows what they are. They had predominantly been found in archival searches of optical survey data, and so their true nature was not really known. And 18 Cow was way up here. So clearly one of the fastest, most luminous transients to date, discovered basically immediately. And so this gave the opportunity to get a better understanding of this part of parameter space in general. And just for your sort of physical intuition, why you might want to learn about this part of parameter space, you can draw a line roughly here in this diagram where optical transients down here have light curves that can be explained by the conventional mechanism of radioactive decay, whereas the ones up here cannot. So the hope was that 18 Cow could teach us something about what this powering mechanism might be. And I want to just acknowledge that many people in the transient community worked on this source. There was a massive worldwide multi-wavelength observational campaign. Also, many people provided interpretations of the data. I don't have time to do justice to all of this work today. I'm just going to focus on my own particular work on the source, which was initially inspired by the fact that I thought that this was some kind of extremely nearby and exotic GRB. And I was wrong. It was not a GRB, but it was nonetheless something very interesting. So because I thought it was a GRB, I immediately, within just days, triggered millimeter and radio observations. My goal was to look and characterize for the relativistic ejecta. So now, just to remind you what you want to do, you want to sort of sample the shape of the synchrotron SED. And so, of course, you want observations spanning as wide a frequency range as possible. So I triggered observations all the way from 5 to 340 gigahertz. Now, I also wanted to mention that it's actually historically fairly uncommon to get these kinds of high frequency, what we call millimeter wavelength observations of transients. That's for a variety of reasons. For example, that these kinds of telescopes used to be a lot less sensitive. But nonetheless, that landscape has changed. And what we found with our millimeter observations was extremely surprising and basically completely unprecedented. So this is a plot showing a collage of 100 gigahertz light curves of various stellar explosions, and this is 18 Cow. So I'll just mention a few of the highlights here. The luminosity was extremely high, so similar to relativistic explosions such as gamma ray bursts. It was actually brightening at these frequencies when we first started observing, which to my knowledge is kind of the first time that's been the case for a transient. And the light curve had a very strange shape, so two kind of bumps followed by an extremely rapid decline. And so to try to figure out what was going on, I got several epochs of observations using ALMA. And so this is the spectral energy distribution about 20 days after the discovery. And the peak of the SED was really beautifully resolved by our ALMA observations. Here is 18 Cow in this radio supernova parameter space that I showed you earlier. And I was just kind of surprised, I remember when I initially plotted this, because it was so far away from everything else. It was way up on the upper right-hand side. And so the question is, what does it mean to be on the upper right-hand side of this diagram? So from the kind of framework I showed you earlier, on such a diagram, you can show lines of constant density. This is relativistic explosions, 0.1 C, 0.01 C. And so the shock speed turns out to be about 0.1 C, which is sort of fast, but it's certainly not unprecedented. On this diagram, you can also draw lines of constant CSM density, constant ambient density, which increase to the right. That's these lines here. And so clearly part of the story here is that whatever this was, it exploded in quite a dense environment. But that's not the whole story because it doesn't explain the y-axis. And so in our paper, we provided the first sort of direct physical interpretation of the y-axis of this diagram. We showed that the peak radioluminosity is directly proportional to the energy that's been converted by the shock divided by the shock radius. And so this efficiency does also have to do with the density, because at a higher density, you will more efficiently convert the energy, but it's also related to the energy of the explosion. And so the sort of inference is that this is a very energetic explosion that took place in some kind of very dense medium. And I just wanted to mention, in case there's anyone on the call who has experience kind of modeling synchrotron spectra, that another very interesting thing about getting these high frequency observations is that you end up in a very weird regime of synchrotron break frequencies. And I'm happy to say more about that in the Q&A. Another important clue came from the X-ray observations. So 18 Cow was observed very intensely, particularly by Swift. And this is the Swift light curve shown in black here. So I like to break the light curve into two phases, what I call the plateau phase up to around 20 days, followed by what I call the decline phase, where the transient started showing quite erratic variability. The X-ray emission is very difficult to explain. You can't explain it as an extension of the synchrotron spectrum. You can't explain it as inverse Compton scattering of the UV OIR photons off of the radio emitting electrons. And the timescale variability here sets a constraint on the size of the emitting region that is significantly smaller than the size of the radio emitting region. And so I was sort of putting all of this together, I was sort of forced to conclude that we're actually seeing something else, that somehow at this stage we were seeing the emergence of a more compact source, presumably a newly formed central engine. And if so, that would be extremely interesting because it would suggest that this could actually be a new channel of engine-powered massive star explosions with several very important differences from GRBs. So whereas in GRBs, the engine remains completely shrouded from the observer, in the cow, the engine seemed to be exposed. Whereas GRBs are famously hydrogen poor. We don't see any evidence of hydrogen or helium in their spectra, so these must be fully stripped stars. In the cow, we did see hydrogen in the spectra, so that suggests that these are a completely different kind of progenitor, and that addresses a longstanding question in the GRB field, which is whether you can get a central engine from hydrogen-rich stars. I mentioned that GRBs, the engine in GRBs launch these ultra-relativistic outflows. In the cow and some similar events that have been found since, it seems that these engines only accelerate material to around 0.5 or 0.6 C. So so that was the picture that kind of had started to come together after 18 cow itself. But then, of course, after that, I really wanted to find more. So I devised a strategy for doing this using the ZTF data. And it turned out to be actually even harder than finding afterglows. You'd think it would be easier. I thought it might be easier because cows are a bit slower than afterglows, and we find them at somewhat lower redshifts. But the problem turns out to be the color. So cows are blue because they're thermal emission, and it makes it extremely difficult to distinguish them from the primary false positive in the search, which is stellar flares. So to some extent, I've found that some brute force spectroscopic classification has been required to find more, but actually this has been very fruitful because it's mounted to the first kind of systematic spectroscopic classification of these mysterious F-bots. And I don't have time to talk about this, but a long story short, most of them turn out to be actually established classes of supernovae. So from these searches, we have found several new members of this class, shown in the center of this diagram here. So from the ZTF data, we found two events, which we nicknamed the koala and the camel, nicknamed that after their ZTF names, in keeping with this kind of explosive zoo theme. And by applying this kind of well-defined criteria to the data, I was able to show that these are quite rare. So the rate is similar to actually the GRB rate, about 0.1% of core collapse supernovae. By cross-matching data from eROSITA, this X-ray mission with ZTF, we identified an additional event, and this was recently published by a graduate student I was working with, Yuhan Yao. And finally, an additional event has been published that was actually found in Catalina Sky Survey data in 2016. So that's the crew of these objects. It's been really, really beautiful to see us fill in the upper right-hand side of this radio transient parameter space. Now, I want to say a bit more about interpreting the millimeter and radio data, because there are a lot of puzzles that I would say are still unresolved. So this is a figure sort of summarizing these puzzles. What you're seeing here is so frequency on the x-axis. So these are spectra, or SEDs. And basically over time, the SED starts up here, and then it cascades down to lower frequencies and lower fluxes. So now at late times, the evolution of the SED sort of nicely follows a power law. So it's power law shifting, where the peak, flux, and frequency also move as power laws in time. But clearly, when you try to extrapolate this model to early times and high frequencies, it breaks down. So that's one problem. There's kind of a high frequency millimeter wavelength bump. Another problem is the spectral index. So the spectral index, I mean the above peak spectral index, so the one here. So for normal supernovae, and also actually for 18 cow at late times, the spectral index is about -0.5 to -1. But at early times, from these high frequency millimeter wavelength observations, I found a much steeper index, something actually very close to -2. So how can you get such a steep spectral index? So I've worked through and explored several different possibilities. I don't have time to get into all of that now. What I concluded was most likely is actually that we're seeing a different population of electrons than what we see when we observe normal supernovae. So let me explain what I mean. So when we model the radio emission from supernovae, we have to make an assumption about the energy distribution of the electrons. And the conventional assumption is that all of the electrons are accelerated into a power law distribution in energy. So this is the distribution, so energy or Lorentz factor, you can kind of trade between the two. Here's our power law, and it has some minimum cutoff value. And the index of this power law from sort of basic physical principles, this kind of famous Fermi acceleration mechanism, is thought to be around 2.3. However, it's actually more natural to expect, and basically always seen in simulations, that only a small fraction of electrons end up in the power law, and actually the majority end up in a thermal distribution. And we call this a relativistic Maxwellian. Now, this very naturally gives you a steeper spectrum. It's actually an exponential in frequency, not a power law. And this kind of thing has been explored in various different contexts in the literature, in the context of GRB afterglows, and also actually Sagittarius A star, which also has a kind of millimeter bump. But to my knowledge, it's never been kind of definitively seen and modeled in observations of a transient. But it does a really beautiful job of describing the data. So this is not a power law. This is a relativistic Maxwellian with self-absorption. And so a couple things to mention. So the exponential does actually a very nice job of describing the very steep spectra that we observed. The optically thick spectral index ends up being nu squared. That's what you expect from a thermal, a thermal distribution of electrons, whereas the non-thermal would be 5/2. You can get very reasonable shock properties by modeling the objects in this way. And the really elegant thing is that it also gives you a direct way to estimate the fraction of electrons that end up in the power law versus the Maxwellian. And so, for example, for this object, for the camel, I estimated that the fraction in the power law couldn't be more than about 20%. Okay, so the troubling thing about this, even though it looks nice, is sort of why we don't see this in other radio transients. Subsequent theoretical work by Ben Margalit, my office mate actually at Berkeley, and Elliot Quadart, were able to explain this. So they've shown that actually the reason we expect to see the Maxwellian in these events and not others is primarily due to the shock speed and sort of secondarily due to the ambient density. So basically, the shock speed sets the electron temperature, and this in turn sets the prominence and detectability of this Maxwellian. And so I've gone through, and so I should say that these cow objects, they're faster than ordinary supernovae. So 0.1, 0.3, 0.6 C, whereas ordinary supernovae are significantly below 0.1 C. And so that's why we're able to see the Maxwellian. So I've combed through the literature and found basically every other object that fulfills these criteria to check whether we can test this hypothesis. And the problem is that none of them have sufficiently high frequency observations for us to see whether there is this exponential cutoff. And so we need more observations of mildly relativistic explosions, particularly with observatories such as ALMA. I think it's very exciting because the implications are that these kinds of high frequency observations can actually teach us something about this kind of fundamental mechanism of particle acceleration. Now, what I've been doing so far is very biased, and I've been getting millimeter observations of optically discovered transients. And so I make an assumption about which transients are worth following up. What I'm really excited about is that now and into the next decade, we have our first blind time domain surveys at submillimeter wavelengths. So I organized a workshop last year to bring together various collaborations and sort of understand the status of these surveys. And so just to report back to you some of what I learned. These searches so far are finding that the dominant transient in the millimeter sky is stellar flares. That's very familiar to me coming from optical transient astronomy. But also these surveys have started to find mysterious extragalactic transients, which I think is very exciting. So I'll tell you more about these surveys using this diagram here. This is a kind of classic diagram used to compare the capabilities of different radio transient surveys. On the x-axis, you put the limiting sensitivity, the flux density threshold, and on the y-axis, you put the number of sources in the sky brighter than that given sensitivity threshold. And then you can draw tracks corresponding to the rates of different known classes of extragalactic transients. And then you can put each survey on this diagram here. And so the SPT, the South Pole Telescope, they've been finding transients that are more common than any class that we knew about. And the ACT, they have not yet completed a systematic search of their data, so I'm just representing them here as an upper limit. Right. And so what's going to change in the next few years is that we'll finally have surveys that are sensitive enough and cover enough of the sky to really push into the regime where we expect to detect a significant number of these known classes of extragalactic events. And I just wanted to mention that the decadal survey highlighted this kind of time domain astronomy as a particularly exciting science aspect of this cosmic microwave background experiment. So I've been getting involved with these surveys, chairing a new transients working group in CMBS4, and I'm really excited for what we'll be able to discover. Okay, so that brings me to the end of part 2 of my talk. I think a lot of exciting prospects for submillimeter time domain astronomy in particular. And so I just have a few slides now to summarize before I take questions. I've shown you how today the time domain astronomy landscape is at least numerically really dominated by optical surveys. In the last few years, we've had the opportunity to kind of chart new parameter space, particularly the fastest optical transients. And these have taught us a great deal about very extreme phenomena, such as relativistic explosions. And then actually something else I'm interested in, which I didn't have time to talk about, is also the sort of death omens of massive stars. But for me, the ultimate goal is to kind of zoom out from these short time scales and connect the exotic transients that we're finding to this story of stellar evolution. And I think we're at the stage now where we've made so many discoveries in the last few years, we kind of need to now take a step back and try to consolidate what we have found in collaboration with our theorist colleagues. And so with that in mind, I'm helping to organize, we've proposed to have a workshop next year that would be focused on these kinds of fast transients and what they can teach us about stellar evolution. So in the next few years, time domain astronomy is really going to explode from primarily being in the optical band to spanning really the full electromagnetic spectrum. I'm particularly excited about these X-ray surveys so we can learn about these low luminosity GRBs, and also these millimeter surveys so that we can get a less biased view of which objects have this kind of luminous millimeter emission. And all of these surveys will be really excellent for the study of stellar death. And in using this data, all of our tools from optical time domain astronomy will be widely applicable. So how to find transients, how to recognize the interesting ones, and how to conduct a follow-up observational campaign. So with that, I will just leave up a summary slide of some of my particular scientific interests.